So welcome to MIT Innotherm. This is our colloquium number 8. And in today's colloquium, we have a really very exciting panel on high thermal conductivity materials. We actually did a survey before on topics are interested. If I recall, this topic were most popular. And so we have a really very exciting panel. And I will leave Zhiting to introduce the rest of the panelists. And let me introduce our moderator, Zhiting Tian from Cornell University. Zhiting is currently associate professor at the Cornell University. My understanding is that she just received a tenure this year, so congratulations. And she has received very distinguished awards. She's a fellow of ASME and the recipient of the Office Level Research Young Investigator Award, National Science Foundation Young Investigator Award, Career Award. And her research areas are tunable thermal materials, thermoelectric energy conversion, thermal transport in soft matter, synchrotron X-ray measurements. And with that, I will stop sharing, and Zhiting, you can share your screen. I'll also go background. Zhiting, you are muted. You are still muted.
Yeah. Okay. Thank you very much, Gang. Hello, everyone. It's my great pleasure to moderate today's panel discussion on high thermal conductivity materials. We are delighted to have 4 distinguished researchers joining us today. Now, let me briefly introduce them in the order of their presentation. First comes Professor Bara. Professor Bara is a professor of mechanical engineering and materials at Georgia Tech. He's an AAAS fellow and a recipient of the prestigious Alan T. Waterman Award from National Science Foundation. And his research focuses on nanostructures and devices for thermal applications, particularly those based on carbon nanotubes and polymers. His research has produced 2 startup companies. Besides being an excellent researcher and educator, Bara is also an award-winning public speaker. I can't wait to hear his talk. Next, Professor David Broido. Professor David Broido is a professor and graduate program director of physics at Boston College. He's an APS fellow. He's a co-PI on the ultra-high thermal conductivity Muri project. David is a pioneer in first principle calculation of phonon transport. In 2007, he published the seminal work on intrinsic lattice thermal conductivity of semiconductors from first principles. It was amazing and inspiring to see the power of first principle calculations as we saw the calculated results for on top of the experimental data. His research area also expanded to the phonon and the electron transport in novel materials. And next, Professor Yongjie Hu. Professor Yongjie Hu is an associate professor at UCLA. Yongjie and I had 2 years overlap in Gang's group. I remember that he was in the clean room day and night making nanostructures. Luckily, Gang has enough funds to cover his user fees. Yongjie has received numerous awards, including the Sloan Research Fellow, NSF Career Award, and Air Force Young Investigator Award. His research areas span from thermal science, nanotechnology, to manufacturing and electronics. Dr. Sara is a staff scientist at Sabic, Netherlands. Previously, she was in academia for more than a decade. Her recent awards include Knowledge Transfer Research Award and Class of 2002 Award. Given her strong chemistry background, her research centers around processing structure and property relation in polymers. Before I hand it over to our panelists, let me quickly go over today's agenda. So each panelist will have about 10 minutes to give their presentations, and we will have about 30 minutes for discussion. And we will have 2 polls in between. To submit your questions for the panelists, please use the Q&A button, and we will be pulling from that stream. Questions are only visible to our panelists. So please note that today's colloquium is being recorded and will be posted on YouTube. For the questions that we cannot get to cover today, they will also be posted online for broader discussion. By default, we will read out your name with your question. If you prefer not to, please state so and we will honor your choice. Now let me start our poll number 1. Okay. Can you see the poll?
Yes.
Okay. So this is the question is, which material do you think is most promising for future applications? So multiple choice, feel free to select as many as you wish. And please scroll down because the last one material you see should be silicon carbide. For those who are on the phone, cannot see the screen, let me quickly just read out the materials we have here. Graphene, carbon nanotube, diamond, cubic boron arsenide, cubic boron nitride, boron phosphide, oriented polyethylene, conjugated polymers, copper, silicon carbide. I will just give it a few seconds. Okay, I'm ending the poll now. So let me sharing the results. So we have 51% on graphene. And then it follows by carbon nanotube, 35%, silicon carbide, 34%, and a few others. Others seems to be around the 20% range, except boron phosphide. Thank you everyone for taking the poll, and we will have it again and towards the end. Now today in the panel discussion, Bara will start to give us an overview from the application perspective on thermal interface of electronics. And then David and Yongjie will talk about the crystalline materials from theoretical and experimental point of view. Last but not least, Sara will cover thermal conductivity of polymers. With that, let me turn it to Bara. The stage is yours.
Thank you, Zhiting. Can everybody hear me?
Yes.
So what I'd like to do is just start off by basically timing myself so I don't go over time and talk too much, but also to really set the stage for why thermal materials are so important. We're really at an inflection point in the world where it's clear that we live in a digital world. Electronics are everywhere. They're in industry, in space, in health devices. And they all have a natural heating problem. And what's happening is that when you think about what people are doing to put systems together today, they're integrating more components in different ways and adding complexity to the package size and design. And so when you think about the thermal interface limits all electronics to some degree, whether it be from an assembly standpoint or a heat dissipation standpoint. It's not always about having the highest conductance. Sometimes it's just about having reliable integration. But if we take a step back and we think about how this drives performance, ultimately we're trying to minimize the loss of temperature at the convective surface to drive heat into the ambient. And the typical flip chip package, as shown here, is going to have two interfaces. One that's commonly referred to as the TIM1, that's going to be closest to the heat source or at the backside of the die. And then it's going to engage it to this heat spreader, typically nickel-plated copper. And then there's going to be another thermal interface between it and a heat sink that could be made of aluminum or copper. And when you think about this, these interfaces often comprise the majority of the resistance in the package. Especially being so close to the heat source here, you really need to optimize them in order to minimize your losses. And so what you look at is you look at thermal conductivity, right? Clearly you want materials that have the highest thermal conductivity, but a lot of times when materials are high in thermal conductivity, they may not have the other features that you need in terms of making mechanical contact or being able to withstand temperatures. One of the prevailing trends is that devices need to operate in wider temperature ranges from used to be -25 to maybe 125, now -55 to 175 for automotive applications, for industrial applications. One thing that people often overlook, though, is the assembly and integration. If we think about trying to take what we do in advanced materials and put them into practical applications, they have to some degree, be drop-in replacement. So they have to look like the form factor that fits into the manufacturing. And so I'll touch on that a little bit more on the next slide. Here's an example of a, however you want to call it, kind of a system in package or system on chip, where this is kind of the new heterogeneous integration roadmap moving forward to be able to put GPU, processor, connectivity all on the same die. And it's mainly designed to drive electrical efficiencies and make things be more efficient in frequency and clock speed, but it creates these tremendous interfacing problems where if you have one material, it may need to make contact with chips that are different heights. So it just can't be a compressible material, but it has to be a conformable material. It has to be reliable, and there are different things related to the different chips in terms of their heating profile that material also has to address. So when you think about this, what in my experience, mechanical features often become the dominant feature. So no matter how high you engineer thermal conductivity, if you can't have the right contact mechanics or deformation mechanics, then it's hard to address these problems. And so carbon nanotubes, organic materials, aligned materials are a very promising class of materials to look at, mainly because you can orient the heat in the direction of heat travel through the interface, but also, as this video will show, that you can have very unique deformation profiles. And so what's unique about that deformation is that it's local. And that's important because if you want to have a dry material, you want to get away from liquids that have problems with addressing thermal interfacing with the current industry trends. And specifically, as package sizes get larger, the thermal expansion causes more shear stress in the interface, and greases and PCMs or phase change materials tend to lose reliability. They tend to pump out more, shear out more. And so as you have larger packages, having a dry material is important. But if you take a normal silicone pad or a piece of graphite and you compress it, it's going to compress more like a trampoline. You're going to push down in one area and it's going to pull material away in other areas. And that creates two problems. One, it minimizes the amount of contact you create for a given amount of deformation. And two, depending on the location of the fasteners, if you press down on the perimeter, the material will bulk up in the center and distort your package and cause stress. And so having this type of unique local deformation, as seen here with the aligned carbon nanotubes, allows you to address these issues in an effective way with a very high conductivity material. So the other issue I'd like to touch on are hotspots. I mean, clearly, this is an IGBT module at the left, and clearly hotspots are in a lot of different devices, but in these devices for DC, AC to DC, DC to DC converters for electric vehicles and clean energy, they're tremendous. But it's not just about thermal conductivity. So we spend a lot of time looking at graphene and 2D materials that can spread heat effectively, but we also need to be thinking about thickness, proximity, and interfaces. And what I mean by proximity is that how close can you put the spreading to the heat source? And whenever you put it close to the heat source, you're going to have to interface it. And the interfaces can be a barrier or an opportunity in how you do the design. And I'll give a practical example. When you look at graphite, which has been something that have been in Samsung Galaxy phones, iPhones, and tablets, oftentimes in industry, people have to use adhesives to laminate 2 or 3 layers of graphite together to get practical performance. Mainly because you need to have some cross-sectional thickness to the spreading material in order to be able to get the heat out effectively for the system. So, as we develop these 2D materials, the way we layer them and integrate them and how it preserves the thermal conductivity and system level properties are just as important as having very pure high conductivity materials. Here's an example of things that researchers have been looking at for some time now to be able to put heat spreading close to the hotspots. So here you have a GaN device. Diamond, which is a known very high thermal conductivity material, is grown on the backside or it's adhered. But this highlights these issues and these challenges that we have in terms of diamond may have a very high conductivity, but you have to have an adhesion layer or there's an interface and it will dictate its ability to spread effectively. And so these are the opportunities that we have in both thermal interfacing and heat spreading. And in many ways, they're inextricably connected because to spread heat, you must interface. And to interface, you must ultimately reject that heat somewhere. And there are a lot of opportunities in looking at materials like aligned carbon nanotubes, two-dimensional materials separately and together to find very efficient combined solutions. So this is my last slide. Hopefully that was helpful to introduce the basic application space that motivates a lot of the work in thermal materials. Zhiting, I'll pass it back to you. And
thank you, Bara, for the very exciting presentation. Now let's pass it to David.
Okay, I hope everybody can see my slides. So I'm going to talk about kind of a complementary focus where we're going to really just try to understand better ultra-high thermal conductivity materials and try to identify new such materials without really worrying about how they can actually be incorporated in devices. As Bara mentioned, there's lots of challenges connected to that. But the plot that you see is showing the measured thermal conductivities at room temperature for a collection of high thermal conductivity materials as of, say, 10 years ago or so. And what really stands out in the plot is that diamond's thermal conductivity is by far the highest, considerably higher than some of the other materials that you saw on some of Bara's charts involving, say, copper and aluminum. Diamond is an electrical insulator. The best metals, copper and silver, have 5 times lower thermal conductivity. So, you know, we want to see what we can learn about why diamond's thermal conductivity is so high, and are there other materials that can approach its high thermal conductivity. And of particular interest to us, which I'll come back to later, are the 2 boron compounds, boron phosphide and cubic boron nitride. So I'll talk about those at the end of my talk. Okay, so diamond is a crystalline insulator, so we're going to be interested in studying thermal transport and insulating compounds where heat's carried by phonons. We're going to ignore the effect of extrinsic defects like impurities and boundaries that can scatter phonons, and focus instead on just the intrinsic thermal resistance that's produced by the interaction between phonons, which comes from the anharmonicity of the interatomic bonding potential. And to lowest order, this interaction is between 3 phonons, and that tends to dominate the thermal resistance. So that's going to be our focus for a lot of the materials we've studied in any case. And we use a first principles theoretical approach, which I won't have time to describe in detail, but it allows us to extract the ingredients necessary to calculate the thermal conductivity, like phonon lifetimes and phonon velocities. And an example of our early work is shown in the plot, which gives the calculated and measured thermal conductivities for diamond. And you can see that there's very good agreement between the theory and experiment. And that's been now shown for lots of materials by lots of different groups, that we consistently get good agreement with in comparing the theory to experiment. The theory has no adjustable parameters, and so that means that it has predictive power. So we can look at materials where maybe the thermal conductivity hasn't been measured and make some predictions about what those values should be. Okay, so the conventional criteria for achieving high thermal conductivity were put forth by Glenn Slack some 50 years ago or so, and they're listed here. There's these 4 criteria, and they all point to diamond as being an excellent thermal conductor. It's got light carbon atoms and strong covalent bonding, and anywhere you go on the periodic table from there, either going down, which increases the mass, or going away from the group 4 column, which weakens the bonding, necessarily lowers the thermal conductivity according to the conventional criteria. And so that points to diamond as being the best thermal conductor. But it turns out there's another way of achieving high thermal conductivity, and that involves engineering the vibrational properties of the material so as to reduce the 3 phonon scattering. And so this actually involves combining heavy and light atoms, so that goes against the conventional criteria. And the best example of this paradigm for achieving high thermal conductivity that we found is cubic boron arsenide, which combines a arsenic atom with the boron atom, where arsenic is 7 times heavier than boron. And it turns out that there are features in the phonon dispersions of boron arsenide, which are shown in the left plot. There's a collection of such features that conspire to give very weak 3 phonon scattering rates for a frequency region circled in the center plot. And that means that those phonons in that frequency region can carry a lot of heat, and our predicted thermal conductivity for boron arsenide that we published 7 years ago or so was comparable to that of diamond. So this was a quite surprising and exciting result. But it turned out, as was pointed out by another group, that because the 3 phonon scattering is so weak, that means that the higher order processes, 4 phonon scattering, can actually play a significant role in suppressing the boron arsenide thermal conductivity, as shown in the right-hand plot. And at room temperature, the values that we originally predicted are suppressed down to around 1300 watts per meter Kelvin when including the 4 phonon scattering, which is still an exceptionally high value. And in fact, since that time, our recent calculations on lots of different materials show that in fact the 4 phonon scattering in boron arsenide, while it's extremely important, it's actually very weak. And if not for that fact, then the thermal conductivity would have been suppressed a lot more. So these predictions of high thermal conductivity for boron arsenide have now been verified in 3 separate recent measurements. Yongjie will talk about his group's work next, and the group that I was involved in is the first listed paper, and the thermal conductivity versus temperature is presented in the plot. And it's a busy plot, so please focus on the red points, which give the measured time domain thermal reflections, thermal conductivity values. And these are quite high values that are measured. So at room temperature, this high 1300 watt per meter Kelvin value is in fact confirmed by the measurements and in agreement with the theoretical calculations given by the red curve. So this agreement between theory and experiment then validates this new paradigm for achieving high thermal conductivity and identifies boron arsenide as a new unconventional ultra-high thermal conductivity material. So while the thermal conductivity is not as high as in diamond, boron arsenide does have some advantageous features. So Bara talked about the importance of thermal expansion coefficient. In fact, in boron arsenide, the thermal expansion coefficient is actually closer to the common semiconductors used in electronic devices compared to that of diamond. And so this gives it an advantage in terms of heat spreader applications for thermal management. Another interesting feature of boron arsenide is that it's a semiconductor, unlike diamond, which is an electrical insulator. And it has high predicted mobilities for both N-type and P-type doping, which is quite unusual. And so that suggests it's possible to use as a functional material in electronic devices where its thermal conductivity is 8 times higher than that of silicon. Okay, I mentioned these 2 boron-based materials, cubic boron nitride and boron phosphide, on the first slide of my talk, and I want to come back to those now as we've been involved in research on these 2 compounds. Cubic boron nitride is similar to diamond in being composed of light atoms and having strong bonding. And so one might think from the conventional criteria, its thermal conductivity should be as high as diamond, but in fact it has a large isotope mixture on the boron atom, 20% boron 10 and 80% boron 11. That large isotope mixture presents as random mass fluctuations that scatter phonons and lower the thermal conductivity. And so the top plot is showing our measured and calculated results for a collection of boron nitride samples in which the isotope mixture is varied on the boron atom. And so you can see at the 20% mark, the naturally occurring boron nitride has thermal conductivity that's quite high, approaching 900 watts per meter Kelvin, higher than what was measured in earlier work that I presented on the first slide. But upon isotopic enrichment, where we make either almost 100% boron 11 or 100% boron 10, so at either end of the curve in the top plot, you see the thermal conductivity increasing dramatically, almost by a factor of 2 to over 1600 watts per meter Kelvin. So removing that isotope disorder gives dramatic increase in the thermal conductivity to exceptionally high values for isotopically enriched boron nitride. In boron phosphide and boron arsenide, shown in the lower plots, the enhancement is significantly smaller, although in boron phosphide, the thermal conductivity is enhanced from an already high value of 500 by about 20% to over 600 watts per meter Kelvin. So where does that leave us? So in 2020 now, we've still, diamond has the highest thermal conductivity, but we've at least made some contributions in identifying 3 boron compounds whose thermal conductivities are also exceptionally high. In particular, boron arsenide has this very high value and is interesting because it achieves ultra-high thermal conductivity in this unconventional way. Actually, in both boron arsenide and boron phosphide have advantageous properties for applications compared to diamond. So even though their thermal conductivities are lower, they may still be quite useful in applications. And just one final point, which is from our recent calculations on a number of materials, we feel that in achieving ultra-high thermal conductivity in future materials, this is going to be unlikely unless these materials involve the elements boron, carbon, and nitrogen. So just before I stop, I want to acknowledge that a lot of this work has come out of an ongoing ONR ultra-high thermal conductivity MURI program, which is a highly collaborative program involving synthesis, characterization, and theory, and lots of contributors from multiple universities, national labs, and industry. And in particular, I want to acknowledge members of my own group, Navneet, Chenhua, and Makib. So let me stop here and then turn it over to Yongjie.
Okay, thank you. Thanks, Kang, for the invite and putting this panel together. So the two previous speakers had made nice discussions on thermal management applications and the theoretical calculations. I will briefly discuss our efforts in experimental development for high thermal conductivity materials, from chemical synthesis to physical calculations and some device demonstration. So let's first look at the materials roadmap in terms of different thermal conductivity. So I plotted available materials from left to right, the thermal conductivity increases. So you can see that most metals and semiconductors have thermal conductivity in the range for tens to a couple of hundred watt per meter Kelvin. For high thermal conductivity, the current industrial standard is copper and silicon carbide, both around 400 watt per meter Kelvin. So for thermal conductivity values beyond 400 watt per meter Kelvin, that's the region we are searching for new high thermal conductivity materials. Currently, we have only limited options. Diamond and cubic boron nitride have high thermal conductivities, as discussed by the previous speakers. The challenge lies in the slow growth rate, high expense, and also mechanical and other compatible for semiconductor integrations. And the other option is carbon-based nanomaterials, such as carbon tubes and graphetes. They have attractive high thermal conductivity for individual devices. The challenge is when you assemble them together, there's degraded thermal conductivity due to ambient scattering, and also the intrinsic anisotropy due to van der Waals bonding leads to low thermal conductivity and mechanical property in cross-product direction for graphite. So when we started this, there's an urgent need to look at to search for new high thermal conductivity materials, also with compatible processing and integration probabilities. So the boron compounds that we predicted are attractive candidates, but when we look at that, their high quality crystals were not existing in nature. So we have to start from synthesis. So the first candidate is cubic boron phosphide. So my group was able to develop multi-step solution reactions to achieve high quality crystals. And we have did thermal transport measurement. The thermal conductivity for boron phosphide is around 500 watt per meter Kelvin for natural abundance and 600 watt per meter Kelvin for isotope pure, exceeding the industrial standard and most metals and silicon carbide. In addition to high thermal conductivity, the technology advantages of boron phosphide also include high chemical inertness and nuclear refractive. They also have good mechanical properties such as large elastic modulus. There are other applications such as radiative detectors and electronics. The other candidate is cubic boron arsenide. Boron arsenide is more attractive as initial prediction by David shows very high thermal conductivity, more than 2000 watt per meter Kelvin, even possibly exceeding diamond. So we did preliminary synthesis. We made inch-size thin film of boron arsenide and verified the crystal structure in the Raman spectroscopy and XRD. And also we did initial thermal measurement using ultrafast pump probe spectroscopy. The measurement of the initial sample gave a thermal conductivity value around 190 watt per meter Kelvin, which is already higher than silicon, but still much lower than the theoretical expectations. Fortunately, we soon understood that there is strong effect from the defects on thermal conductivity that enhance the phonon scattering to reduce the thermal conductivity. Even there's 0.1% of vacancy defects verified by XPS that can strongly reduce the thermal conductivity by over order. So my students, then the key challenge is to minimize defects to increase thermal conductivity. So my students have carefully controlled the synthesis conditions, including temperature, flow rates, substrates, epithelials, and so on. So we're able to make gradual improvement of the thermal conductivity values from initially 190 to 300, 500, 1000, 1100, 200, and eventually 1300 watt per meter Kelvin. We also made careful verifications over 100 samples and get consistent results. In the meanwhile, we did careful structure calibrations. As shown here, the top row as single crystal XRD diffraction patterns and also the constructed reciprocal space. From both images, you can see this indicates the whole sample is an entire single crystal domain without dislocations or grain boundaries. The bottom row is high resolution TM image, shows atomic resolved lattice without defects. So the crystal is really high quality approach defect free under instrument resolution limit. So then the question is why for this such a high quality crystal, thermal conductivity is still lower than the initial theoretical predictions. So to make long story short, by comparing experiment with different ab initio calculation results, we found that the 4-phonon process is very strong in these materials. So the black dashed line is a 3-phonon theory, and blue dashed line is 3 and 4-phonon theory computed by Shungan's group and Lucas. So we did experimental measurement for boron arsenide from 300 to 600K plotted in the red symbols here. From this comparison, you can clearly see that experiment agrees very well with a 4-phonon theory. So this indicating that there is strong 4-phonon scattering near room temperature in boron arsenide, which however was negligible in most other materials. This also indicating the crystal has very high quality approach defect free. We also performed spectroscopy measurement of phonon mean-free paths. So phonon mean-free path is a very important parameter that describes average distance for phonon to travel before scatters. Usually, a longer phonon mean-free path would expect high thermal conductivity given other parameters are fixed. So I developed this spectroscopy technique with GAN. Essentially, we're using laser spot size, reducing the heating areas to probe the nanoscale ballistic thermal transport and measure the mean-free path. Later on, my group has did careful examination by solving 3-dimensional Boltzmann transport equation. So we understood that, as shown in the bottom left figure, so we plot out plane and in plane heat flux during this measurement configurations as a function of different heating size. And you can see the out plane heat flux remains the same for different heating size, but in plane reduces when you reduce the heating size. So that indicating the measurement actually has in plane suppression of heat flux to probe the ballistic transport. So we will apply this spectroscopy technique to boron arsenide, diamond, and cubic boron nitride, and made the size-dependent thermal conductivity plotted in the right figure. As you can see, when we reduce the heating size from 100 micrometers down to 1 micrometers, the thermal conductivity of all the 3 materials reduces as expected due to the ballistic thermal transport. However, in particular, boron arsenide has the largest reduction up to 50% when the heating size is reduced to about 1 micrometer. So this indicating that in boron arsenide, there's a large portion of phonons have very long mean-free paths over microns even at the room temperature that contribute to about half of the total thermal conductivity. So this measurement verifies a very long phonon mean-free paths in boron arsenide due to its unique band structures, also explains the origin of high thermal conductivity in boron arsenide. So we made here the 3 prototype high thermal conductivity materials. And you can see that the thermal conductivity of boron arsenide is over twice that of cubic boron nitride and only exceeded by diamond. So the high thermal conductivity of boron arsenide has also been verified by collaboration teams involving Gang and David and several other groups. So if you think about the general definition of common semiconductors, then boron arsenide is established as the best thermally conducting semiconductor. I emphasize here that being a semiconductor, it has advantage for integration with electronic devices, such as other compatibility properties in mechanics and thermal interfaces. So with these materials in hand, now look back to the initial motivation for thermal management. So I don't mean here to look at the fundamental mechanism that contributes to the near junction thermal resistance. So the near junction thermal resistance could come from several different parts. It can come from interface scattering. That's kind of intrinsic due to the energy spectrum mismatch across the interface. It would exist even there's atomic perfect interfaces. It could also come contributed by incomplete contacts such as voids and surface interface roughnesses that reduce the effective contact area. The other contribution to thermal resistance is the disorders near interfaces. For example, when you bring gallium nitride, you usually need sacrifice layers required to improve electronic quality. However, the sacrifice layer also has defects in the lattice that introduce low thermal conductivity. So during last decades, there's a very interesting proposal using high thermal conductivity diamond as cooling substrate to improve thermal management. There's many exciting progress from varied groups, including Goodson, Sammy Graham, Avi Bakohan, and so on. The interface between diamond, however, was found to be poor with GaN layers. So as mentioned, boron arsenide is a semiconductor, so it has compatible mechanical properties and energy spectrum matchings. So that would expect boron arsenide might have a better chance in terms of enhance the thermal transport measurement. So the important for the next is to experimental integration and measure the thermal management performance. So indeed, my group recently was successfully integrated nitride and boron arsenide. And we made the near junction thermal resistance is significantly improved over that with diamond. And also when you further integrate boron arsenide with high power device during its operation, can clearly see that the hotspot temperature was significantly reduced. So this is a very exciting result. So it verified that from the theoretical prediction to experimental demonstration of the boron arsenide, now we demonstrate that boron arsenide can be used as high performance building blocks to achieve high performance thermal management of power electronics. So in addition to thermal properties, as newly discovered semiconductors, many other properties have not been explored. So we recently developed this experimental database of boron arsenide, measured multi-physics properties, including mechanical and acoustic properties, electron modulus, hardness, the band gap 1.82V, optical refracting index, thermal expansions, and also electronic properties. We hope this study can serve as a starting point to inspire more research in many different areas for this new semiconductor. So with that, I would like to conclude my talk. We developed this high quality crystals and made ultra high thermal conductivity and verify this non-mean pass and the phonon contribution process is important. And we demonstrate device integration and high performance for power cooling. And we expect this could also lead to application in other areas, including electronics, photonics, and mechanics. So thank you very much for your attention. Now I think I should pass to Sara, who's going to talk about high thermal conductivity polymers. Thank you.
Thank you. I'm going to share my screen. Right. Okay, so I will talk about polymers. So I have a bit of a different role today. And in order to do that, I would like to introduce briefly some features of polymers that will be relevant with respect to thermal conductivity. So polymers are basically giant molecules. We're talking about molecular weights over 10,000 grams per mole, composed of a repetition of one or few basic units. And if we are talking about thermoplastics, so polymers that can be processed through a series of melting, through application of heat, and cooling through, so solidifying through cooling, this material basically are composed of long strands with few or no branches. So if the composition of the polymer is uniform and the structure of the basic unit is simple enough, this material tends to crystallize, but it's important to realize that this material can never crystallize fully. So we will never achieve 100% crystallinity in this material. Doesn't matter how hard you try. And most common thermoplastic basically only have covalent single bonds between the atoms of the chain backbone. So basically, saturated polymer have very strong covalent bonds along the chain, but very weak intermolecular forces between the chain. So we're talking, for example, of weak van der Waals forces for polyethylene or polypropylene. And most important, they have no free electrons. So the thermal conduction is only possible through lattice movements, of course, along the chain backbone. So it's important to realize that in polymers, the thermal conduction is by any means anisotropic. Now, the problem is that bulk material, bulk polymer are very disordered. So the thermal conductivity that you can read in a bulk polymer is in the order of 0.2 to 0.3 watt-meter Kelvin. So the point is, how can we improve this order? And there are three main elements to consider. We should have high crystallinity, so we should have a simple repeating structure and a regular structure. We need to have as few chain ends as possible, so we need to have very long chains, and we need to have a preferential orientation of these chains. Now, the crystallinity, so the simplicity of the structure and the number of chain ends is something that you can control from the synthesis, so from the polymerization step. While the preferential orientation is something that you will control later on during the processing, and in turn will also affect the crystallinity of the material. So that the orientation in polymer could induce higher thermal conductivity is something that was already proved in 1977 by Choi. He realized that extruded polyethylene of high to medium molecular weight was showing anisotropy of thermal conductivity. So in the direction of the extrusion, the thermal conductivity was reaching 9 watt-meter Kelvin, while perpendicular to it was the normal 0.2 value that you would find in bulk materials. So they were the first to realize that this orientation is important, and they also realized that intercrystalline bridges, what they define as oriented amorphous, so bridges that interconnect crystalline part, are also contributing to the enhancement of this thermal conductivity. More recently, for example, Liu and co-workers have found that the thermal conductivity of aligned electrospun polyethylene oxide could reach value up to 28 watt-meter Kelvin. But the polymer I want to focus on today is ultra-molecular weight polyethylene. So this material is basically an analog of the common high-density polyethylene. So the repeating unit is the same, just CH2, CH2, and it's a linear polymer with no branches, but with molecular weights higher than 1 million gram per mole. So we have the simple structure, we have very few chain ends, we should have everything. So we should have a material that could crystallize very well, could be processed very easily, and could be oriented very nicely. The reality is not that easy, because the crystallinity of ultra is actually lower than the lower molecular weight analog high density polyethylene. And the reason of this is chain entanglements. Basically, ultra, being a thermoplastic, needs to be processed in the melt. And when you go in the melt, all these very long chain tend to entangle so deeply that basically the movement of this chain is very difficult. So you get very high melt viscosity that actually hampers the formation of crystalline portion and hampers also the processing of the material. So the question now is, can we reduce the entanglement? And if yes, does this basically make a difference? And there are several ways to reduce the entanglement. And one of these ways is basically dissolving the polymer in large quantities of a solvent. And when I mean large, I mean over 90% in weight of the solution has to be solvent. And just a 10% of this ultra in a suitable solvent forms a gel that can be spun. And when you spun this gel, basically you induce high orientation and high crystallinity. And using this method, Chen and co-workers managed in 2010 to create a nanofiber of very highly oriented and highly crystalline ultra-high polymer that showed a thermal conductivity of 104 watt-meter Kelvin. And they measured this by basically suspending these nanofibers between a micro thermocouple and an AFM cantilever. So a very, very elegant way to do that. And during my time at Loughborough University, I worked together with Professor Rastogi on a synthetic pathway that allow us to synthesize ultra-high directly with a reduced number of entanglement. So if you synthesize ultra-high using single site catalyst in dilute solution, low pressure and low temperatures, what you get is a disentangled ultra-high that can be actually ultra drawn in the solid state. So you don't need to go in the melt. You can compression mold this material into coherent plate below the melting temperature, and you can stretch this material uniaxially into tape or even biaxially into films, inducing very high crystallization and very high orientation. So when we measured the thermal conductivity of these tapes with in-plane laser flash thermal diffusivity, we found that actually we could reach value up to 65 watt-meter Kelvin when the polymer used had, you can see in the graph on the right, have molecular weight of 10 million gram per mole. So with lower molecular weight, we were reaching up to 45 to 50 watt-meter Kelvin. And it's very interesting to realize that even the biaxial orientation could induce thermal conductivity, and the film were showing an in-plane thermal conductivity of 18.4 watt-meter Kelvin, so in the range of steel. We did some studies in collaboration with Minnick at Caltech, and they used transient grating spectroscopy to evaluate the mean free path of phonon in tapes of disoriented polyethylene. And what they found was that basically the free path of phonon is considerably longer, it's about 100 nanometer. So it's longer than the actual dimension of the crystallites that we evaluate through SACS to be about 50 nanometers. So this confirms, of course, that there is a significant role of this constrained amorphous that bridge the crystalline part. And they also found experimentally how deeply anisotropic is the thermal conduction in these oriented tapes. So to conclude, the thermoplastic polymers can conduct thermal energy through lattice movement, but this only happens through the polymer chain backbone. So if you want to improve this thermal conductivity, you need to reduce the lattice defect. So you need to have high orientation, you need to have high crystallinity and low number of chain ends. So you need also to be mindful that chain entanglements in your material when processing can influence a lot the processability of the material and the orientation, the orientability of the material. In terms of advantages of using oriented polymers, for sure there is the fact that they are lightweight. You can tune the value of K depending on the stretching, and basically you don't need any additional fillers. And of course, the conduction is anisotropic, and this can be an advantage or a disadvantage depending on where is your application. And in terms of disadvantage, of course, there is the problem that polymer have narrow T temperature range of use, and they will lose conductivity if the orientation is lost. So with this, I would like to conclude my part and give it back to Zhiting. Thank you.
Thank you all for the excellent talks that set a great stage for our following discussions. I would like to remind the participants to submit your questions through the Q&A button. And let's start with the first set of questions. The first question comes from Roland Wazaha for Bara. Hi, Bara. How do you address the contact thermal resistance at surfaces between the carbon nanotubes, like the phonon scattering at individual boundaries, and the macroscopic thermal resistance between the carbon nanotubes and adjacent substrates?
Thank you for that question. It's a good question. The way I look at it is that you want to do an order of magnitude analysis to see what's most important and address that first. And typically it's the macroscopic physical contact that you want to maximize. So really what it's really an engineering of the mechanics of the carbon nanotube array deformation. The more you can maximize the morphology such that when the nanotubes deform, the tips can free themselves from entanglement, you're going to get more of the tips of the nanotubes making contact with the physical surface. And so it's a complex problem that involves synthesis optimization, along with studying mechanics. But that's one approach. And my research group has shown in the past that doing things that break or weaken the van der Waals interactions between CNTs, like immersing it in the solvent, allow the nanotubes to flow more freely so they can make contact. Now, when they make contact, you're going to have tip contacts and sidewall contacts, but predominantly you're going to have sidewall contacts. So when you get into thinking about managing the phonon scattering, the phonon velocity is anisotropic across the carbon nanotube lattice thickness. So just, I say that, but in reality, you're still going to, at the nanoscale, have to first solve the physical contact and bonding problem. If a nanotube is just sitting on a surface and it's weakly bonded with van der Waals interactions, it may not matter how those phonons make it to the interface. They may lose a lot of energy transporting across that van der Waals interface. So that's the next thing. So if you can solve the physical macroscopic contact problem by changing and engineering the morphological properties of the deformation process, then when you get into the individual nanoscale contacts, if you can solve the bonding problem, figure out ways to move from weak van der Waals to covalent interactions, then you've solved the next level. And then once you have solved that problem, however you bond them, then you can think about density of states and phonon matching, and just trying to understand that problem. But the first two are so hard that rarely do you get to the third one.
Thank you for the very detailed answer. Let's move on to the second question for Yongjie and David from Lucas Nancy. So why are the defects so important in governing semiconductivity of boron arsenide, but not so in diamond?
David, I will probably just comment that Lucas, I think experimental-wise, people did see degradation in semiconductivity for defective diamond, right? That's also challenging for these groups working using diamond for electronics cooling, especially in the near junctions. The diamond would have high density of defects layers there that significantly reduces semiconductivity from the ideal 2000 down to several hundred even. Actually, the industrial standard diamond is about 1000, even lower than boron arsenide. Only ultra high pure diamond has up to 2000. Right? But David might have more insight from theoretical side. David, you mute yourself. We can.
Let me just second what you said, that diamond has been around for a long time. I think the synthesis is quite advanced, and boron arsenide, there's still a lot of work that needs to be done. But one interesting aspect of boron arsenide is, at least as far as substitutional defects go, is that if you can have the defects on the boron site rather than the arsenic site, then because of its large mass ratio between the arsenic and boron atoms, it turns out that defects on the light atom site will have much less effect on the thermal conductivity than defects on the heavy atom site. In the case of the early samples, I think that Yongjie studied and talked about, where the thermal conductivity was so low, one speculation was that there were arsenic vacancies. And so there you have a defect on the heavy atom site, and that significantly reduced the thermal conductivity.
Thank you both. And the next question is from Carlos Daniel Desmarin. Is there a fundamental limit to how high the semiconductivity of a material can be?
That's an excellent question. I I don't have a great answer to that, but just from the empirical evidence, it seems like it's going to be very hard to beat diamond. I mean, you go by the conventional criteria that were laid out years and years ago. You know, the periodic table is discrete, right? It gives you what it gives you, and you can't make diamond materials that are involve atoms that are simultaneously lighter than carbon and have stronger bonding. So, you know, I would speculate that probably diamond's never going to be beaten. You know, we spend a lot of time thinking about the paradigm that boron arsenide fits, and we really can't see a way of having that paradigm give you a material whose thermal conductivity is higher than diamond, given the discrete nature of the periodic table. So I guess that's the best answer I can give.
Anyone has anything to add? Now, let's move on to the next question. Like we were just discussing the upper limit for a material, and we have several questions on the upper limits of thermal conductivity for polymers. So I can read out one question particularly, but we have several similar questions. This one is from the anonymous attendee. So questions for high thermal conductivity in pure polymers. In reality, rather than simulation, what would be the highest limit to thermal conductivity in polymers, especially highest limit to thermal conductivity in amorphous polymer region? Are the best of polymers now available close to this limit? Or can we expect to see further progress as materials continue to improve without increasing crystallinity?
I think crystallinity is important. For what I've seen in amorphous-oriented polymers, you never reach similar value as crystalline-oriented polymers. So for what I've seen in the literature for oriented amorphous, you could reach up to maybe 10 watt-meter Kelvin, and we are on one order of magnitude higher with crystalline, of course. Now, the highest limit that you could reach, the problem of polymers is that they are not uniform in nature. So they have a distribution of molecular mass, and this is what brings basically the combination of crystalline and amorphous part. So you will never be able to reduce complete or to have a perfect lattice and a perfect orientation. So I think this value of 100, for example, like the nanofibers, are already quite remarkable. And going up over that would mean engineering even more the catalysis part, so trying to create as much as possible molecular weight distribution of polymer that are close to 1. That it's possible, but it's not easy. And then trying to create ultra orientation. And now the orientation is a function of how easy the material can move. So you want something flexible, but at the same time, a flexible polymer may have more difficulty orienting compared to a rigid polymer. So if you compare nylon with aramid, for example, they have the same basic component, let's say, but aramid are rigid while nylon is flexible. And with aramid, you can reach very high orientation, but it's a very complex type of processing that you have.
Mm-hmm. And a kind of follow-up question on that. So we have seen like those very high thermal conductivity from polymers are basically along the polymer chain direction. So we have a question from Jeffrey Vostro. Is there any hope of a polymer with isotropic high thermal conductivity?
You would need to go into not thermoplastic, because thermoplastic by their nature are chain, so you only have weak intermolecular forces. You could go for higher intermolecular forces, but you won't have a covalent bonding. To get a covalent bonding in 3 dimensions, you have to go to thermosetting material. thermosetting material by their own nature are highly disordered. So it's something that may be very difficult to realize, honestly. Yeah.
And one more question for you, Sara, from Richard Zhang. Could the optical virtual properties of drawn polyethylene change?
Yes, they do. And we have recently published on that. So you may find an article that we have published last couple of weeks. So yes, they change, and there is a strong effect of this orientation, this preferential orientation. The biaxially stretched materials show birefringence, for example, and we have done some study adding gold nanoparticles. So when you add gold nanoparticles and you orient the material, you get some interesting effect on the optical properties of the material. Yes.
Thank you. And next question for David from Professor Suiga-Maruyama. Thank you, David. Identifying the boron isotope effect on cubic boron nitride is wonderful, and the boron arsenide discussion is also wonderful. What do we expect from two-dimensional hexagonal boron nitride and hexagonal boron nitride tubes? These are quite important materials for the future. On the other hand, overcoming the natural isotope effect in practical applications seems very difficult. What do you think?
Yes, thank you for that question. That's an excellent question. Yes, in terms of the isotope effect, that's true. If it's, insofar as it's possible to isotopically enrich materials in a cheap fashion, then that would be great. But my understanding is it's actually quite difficult to do that. So makes the boron nitride compound perhaps less interesting from a technological point of view. As far as the hexagonal structures and layered structures goes, it's interesting that the thermal conductivity in those materials, even in the 2D layers, is lower than in the hexagonal boron nitride measured thermal conductivities in the layered structure is lower than the corresponding cubic structure. Same thing if we compare, say, graphite to diamond. In hexagonal boron arsenide, I know there have been some calculations. I think even there they find lower thermal conductivities than in the cubic structures. So not to say that they're not promising, but the cubic structures tend to give the higher thermal conductivities.
So I just want to add that my group at Lux Ninzi did the calculation for two-dimensional boron arsenide. I think we can achieve something. Ab initio calculation shows thermal conductivity up around 400 watt/meter Kelvin. But I guess partially the reason is due to some dynamic stability requirements for two-dimensional. There is a buckling requirement for the crystal structure. So some of the features in the bulk boron arsenide actually disappeared. So that enhanced the scattering there. So we did publish a paper in PIB. Thank you.
Thank you both. Now let's turn our attention to graphene. So we have several questions I will lump together. So Pablo L asked, what about graphene? Could it be a good candidate for thermal management? And another question from Rafat Mahmoud, can the thermal conductivity of graphene deposited on a substrate reach that of the suspended graphene, at least theoretically?
I should probably defer to Bara on the practical aspects, but my understanding is that, so certainly graphene is just a monolayer thick, and so in terms of, say, using it in a heat spreader application, you wouldn't really be able to transfer heat vertically to the layer. You need to have a certain thickness, and since the thermal conductivity is anisotropic and quite low in the direction perpendicular to the layers, then probably it wouldn't be as good for thermal management applications. But Bara, you can probably say more about that.
Yeah, David, I'll add to that. I think that the most promise I see with graphene is in an electronic device that handles self-heating better than other things. You know, as long as you can couple it to a substrate well. But you're exactly right. I mean, in terms of as standalone heat spreading solution, it's very difficult to practically integrate something like that. Ultimately, it just turns out to be graphite. There are a lot of people selling graphene heat spreaders in the market, but it's all graphite based.
Thank you. And then let's talk about flexible electronics. Question from Brandon Smith. What are your thoughts on flexible electronics and the thermal challenges associated with dissipating the heat, which is limited by the polymer substrate? Will flexible electronics ever be viable?
From the polymer point of view, yes, there is this big problem of the loss of thermal conductivity the moment you lose the orientation, and polymer have a sort of narrow range of application. Now for ultra, for example, the moment you go above 90 degrees centigrades, you start losing orientation because of basically movement of the intercrystalline part. A way to fix that is, for example, to cross-link the material. So you cross-link and you sort of fix in space. You go a bit towards a thermoset in a sense, but when you go towards cross-linking, you lose the flexibility. So there is a very difficult balance between being flexible, that means that material can move and can lose the orientation, and being rigid, meaning that the thermal conductivity is there, but the rigidity becomes a problem. So I think it would be interesting to understand material, to expand the study to other type of polymer that have higher glass transition temperature or higher melting. To do that, the structure will, for sure, will be more complex. So this can affect the thermal conductivity, but it's always a question of balancing all these different aspects.
Certainly. Anyone has anything to add?
Yeah, I'll add to that. I'm pretty relatively positive on flexible electronics. I do think there are some applications where they don't operate at such high temperature, maybe in human health and in clothing, wearable things, where both polymer technology for substrating, but also just how you stack it up, because ultimately, when you control the stack up, which will inherently have interfaces, there are ways where you can still leverage heat spreading in a polymer. You know, Sarah's point about the difficulty with getting isotropic thermal conduction. The flexible electronic space is actually more attractive because the anisotropic of the high molecular weight polyethylene could be utilized in space. So there's still work to be done, but I think that when you look at the flexible electronic architectures that are starting to show some promise, carbon nanotubes are actually showing significant promise, you know, in that, and graphene has promise. You can envision integrating some of those things onto a high conductivity polymer heat spreader.
Thank you for your insights. Next question is on 4-phonon model. We have two questions around that. Richard Zhang asked, on the applicability of the 4-phonon model, are there limitations that may overtake its capabilities? Why not a 9,000 phonon model? And another anonymous attendee asked, would a 4-phonon scattering suppress the thermal conductivity of graphene, similar to how it suppresses the thermal conductivity of boron arsenide?
Okay, so I'll try to answer that, those two questions, as they're both great questions. So as far as the first question goes, certainly for the high thermal conductivity materials, which are generally stiffly bonded materials, the atomic vibrations, the amplitude of those vibrations is very small compared to the lattice spacing. And so you can think of the interatomic bonding potential expanded about the equilibrium classical position where all the atoms are just on the periodic lattice sites. And so those displacements are small. And so if you imagine a Taylor expansion of the interatomic potential, the first two terms give you the phonon model, and then the successive terms are the anharmonic terms, and we expect them as we go from third order to fourth order terms, we expect those terms to get successively smaller. So we would expect that the fourth order term is smaller than the third order term, and so generally, certainly in stiff materials, the 4 phonon scattering should be weaker than the 3 phonon scattering. So a 9,000 phonon model, we expect that to be very, very weak. Certainly we can't treat it theoretically. In fact, going beyond 4 phonon model, I think is certainly computationally impractical at this point. And then in terms of graphene, that's a very interesting question. So there's been an interesting publication recently from Zhu and Ron's group, where they actually predict that 4 phonon scattering should be very strong in graphene and lower the thermal conductivity quite a bit. And so I'm surprised by that result, but you know, their group pioneered the 4 phonon scattering calculations, so it's quite an interesting result. And I guess you know, how does it compare to the experiment? I guess the experiments on graphene thermal conductivity are quite variable, and so I guess one could imagine that the jury's still out on whether that theory is correct or not. But insofar, that's the only calculation I know of 4 phonon scattering in graphene, and it predicts that the 4 phonon scattering in graphene is considerably stronger than it is in boron arsenide.
Thank you. And we have another question from anonymous attendee. In addition to polymer melting temperature, what other concerns do you have when pure polymers with high thermal conductivity are applied for thermal management applications? How can we tackle the plastic waste problem?
Yeah, that's a very relevant question, I guess, nowadays. And I think in terms of the plastic waste, I think we need a shift, a paradigm shift, because we need to start realizing that plastic is a resource, should not be a waste. So in that sense, using monomaterial as much as possible, or few material sort of solution, I think is the answer. Because when you have less material composing any technology or aspect, you can more easily take them apart and then recycle or repurpose or reprocess them in some way. And thermoplastic polymer have this advantage. They can be reprocessed as many times as you want in principle. So if you have ultra without any added particles, you can basically reprocess it into other application. So as I said, I think it's a paradigm shift needed to tackle the plastic waste problem. Thank you.
Thank you. We have a question from Adina Li. When combining light and heavy atoms, does the size difference and structural inhomogeneity introduce local stress that affect the performance and stability of the compound? That one was for David.
Oh, that was for me also. So that's something that I think maybe Yongjie could probably comment better than me. So we are always focused on kind of perfect compounds, and we try not to worry too much about those kind of aspects. We haven't actually done any calculations. We always assume pristine materials, maybe with some substitutional defects, but we haven't actually done any calculations of thermal stresses or things like that.
Thank you. And we have one last question for Bara. For the commercial applications of your research, what are the opportunities and the challenges in energy and industrial applications?
Right now, the inverters, DC to DC, AC to DC, are going to much higher frequencies. Those industries are seeing thermal interfacing be a problem like it's never been for them. So, you know, one of the things that's true about thermal interfaces that people sometimes don't know unless you kind of get deep into the practical weeds, there's a class of interfaces that are bolted, that are large, typically metal to metal interfaces. And then there's these interfaces that are spring loaded or use fasteners like you typically see on your PCB board. The mechanics are completely different for those two classifications. It makes it very difficult to use a lot of gasket materials in bolted interfaces because of distortion. So I think a lot of opportunities exist in large interfaces where it's well established by people who are deep in the industry that there's a lot of pressure non-uniformity in the interface, but you need to figure out a way to make good contact and be reliable. And so with these industrial energy applications, the temperature range of operation and in which they need to be qualified is so high as well that traditional materials like silicon elastomer pads will sweat and seep oil and contaminants into their systems, or things like indium will melt. So it becomes very challenging for the industry there. So it's a great opportunity to think of materials that are chemically stable, work in a relatively high or wide temperature range, but also can meet complex mechanical deformation requirements.
Thank you, Bara. So I have a very productive panel discussion. We get to cover the majority of the questions from the participants. I want to offer you an opportunity. If you have questions for each other, feel free to ask now before I launch in the second poll.
I have
Good.
a question for David, yes. Because do you think that this concept of atom of different mass could be applied to polymers? So if we consider a polymer like a silicon polymer instead of a carbon one, do you think it could make a difference in how does the concept that you explain transfer into the polymer, let's say, realm?
Right. So I think it would be very challenging in the case of polymers. You know, the features that give boron arsenate its high thermal conductivity really are intimately connected to its crystalline structure and isotropy. And in the case of the polymers, I don't really see how to, you know, I showed a picture of the phonon dispersions, and there are a combination of features there that are really acting together. It's really quite amazing that nature even gives you a material like that that has these perfect features. So I'd have a hard time imagining in a chain-like arrangement that you could actually reproduce those features that you need so as to minimize this phase space for the 3 phonon scattering. Yeah, so.
Thank you.
Thank you all. And now I'm going to launch the second poll. It's essentially the same question as the first one. We'll just see how our panelists did this today. Let me just read out the questions. Which material do you think is most promising for future applications? Again, multiple choice: graphene, carbon nanotube, diamond, cubic boron arsenide, cubic boron nitride, boron phosphide, oriented polyethylene, conjugated polymers, copper, silicon carbide. Okay, we have about 50% response. Let me wait for a few more seconds. Okay, I'm ending the poll now. to share the results with you. Graphene, 42%. It was the highest from the first poll. And carbon nanotube, 42%, diamond, 31%, cubic boron arsenide is a winner, 48%. Cubic boron nitride, 29%, boron phosphide, 6%, oriented polyethylene, 21%, conjugated polymer, 20, copper, 15, silicon carbide, 22. So, what do you think, our panelists? Are you satisfied with these results?
That's very interesting. We moved them a little bit.
Yeah.
David, move on for commercialization. Zhiting, can I ask one question to Sara, if it's okay? Quick question.
Yes, sure.
So Sara, I'm just wondering, interesting about this high conducting polymer. So one advantage for high semiconductivity polymer is being high conducting and also soft, right? So on the other hand, if you increasing the degree of orders, the mechanical stiffness will increasing. So is there a chart or something indicating a certain correlation between these two?
Yes, basically we have done similar studies of the one that I showed on the mechanical properties. So you see exactly the same behavior in terms of tensile strength and modulus. So you see basically this asymptotic behavior happening exactly the same as a function of the stretching. So the higher stretching, basically you align the chain, you get more van der Waals forces, and basically you get highest modulus and strength. And you can almost plot them side to side and you will see the same sort of behavior.
So in that sense, we also do not want fully crystallized of polymers, right? You don't want, because the mechanical property will be bad.
Will be extremely rigid. Okay, so
okay.
You need a bit of amorphous for compliance.
Okay, thank you.
Okay, I want to thank all our panelists for their insightful presentation and discussions. And I want to remind you of our next colloquium on August 5th. We have Ken Okazaki from Tokyo Institute of Technology on significant role of hydrogen towards sustainable development goals. And we also have an exciting panel. We also have two future events on August 19th on thermal management of electric vehicles, and on September 2nd, Earth energy balance. As always, our organizers value very much your feedback, so please type your suggestions for future events and sign up for an email list for future notice. Thank you all very much for attending today's colloquium, and we hope to see you in 2 weeks.